Hey guys, so today we're going to talk about the Laplace transform, and yes, it's Laplace, not Laplace or Laplace, although it doesn't really matter because however you pronounce it, it's still going to work the same. So, really quick before we start, I'm just going to show what we're going to go over in this video. So we're going to start off with the linearity of the Laplace transform, then show what the Laplace transform actually is, and then we're going to apply the Laplace transform to a few functions. So we're going to do e to the alpha t, cosine of alpha t, and then we're going to apply the Laplace transform to the Dirac delta function, which models like impulses, and then the Heaviside step function, which could be thought of like delays or switches. The Laplace transform is linear, and all that really means is just that if we have the Laplace transform of something like f of t plus g of t, that would be equal to taking the Laplace transform of f of t and then adding that to the Laplace transform of g of t. What that also means is that if we have some scalar alpha times f of t, taking the Laplace transform would result in just alpha times the Laplace transform of just f of t. Alright, so now let's get into what the Laplace transform actually is. So if we were to have some function f of t, what we're going to do is take the Laplace transform of f of t. And this is our input. And our output is just taking this integral from 0 to infinity, and our integrand is e to the negative st times f of t. And this integral is with respect to t. And what's left for us after this is just evaluating this integral. Before we do an example problem, I'd like to point out that there are tables of these Laplace transforms. So you're able to see like if you apply the Laplace transform to some function, then what the output would be. And then obviously from that you could also see like the reverse. These tables kind of have like a general function. So for this example, we're going to take f of t to be e to the alpha t, and this alpha is just some constant. And we're going to be solving it in terms of alpha, so then whatever you encounter alpha to be, you could just plug it in. So now let's get started with this example problem. So we're taking the Laplace transform of e to the power alpha t, where alpha is just some constant. Referring back to what we said earlier, this is just going to be an integral from 0 to infinity of e to the negative st times e to the alpha t dt. From here, we could just rewrite this as an integral from 0 to infinity of e to the power of alpha t minus st dt, and that's just equal to the integral from 0 to infinity of e to the power of alpha minus s times t dt. From here we could see that our antiderivative is going to be 1 over alpha minus s times e to the alpha minus s t, evaluated at 0, and we have infinity up here. If we were doing this completely properly, we would replace the infinity with some variable and then take the limit as that variable approaches infinity. Now from here we have two scenarios. One where this integral converges, and one where this integral diverges. If s is greater than alpha, then this integral will converge. If alpha is greater than or equal to s, this integral is going to diverge. That's just because of this right here. When we have infinity, if s is greater than alpha, then e to the alpha minus s times t will go towards 0 as it approaches infinity. Though if alpha is greater than or equal to s, then this is just going to diverge. So let's just take the case where s is greater than alpha. So evaluating this is just going to give us 1 over alpha minus s times 0 minus, and then e to the power of 0, which is going to give us 1. This is just going to be equal to negative 1 over alpha minus s, which is equal to 1 over s minus alpha. So now if we had any e to the alpha t, we know what its Laplace transform is. So now let's take some alpha. Let's say we had e to the power of, 41 times t. Well, the Laplace transform of that would just be equal to 1 over s minus alpha, which in this case is 41. Next, we're going to do the Laplace transform of cosine of alpha t. So we have the Laplace transform of cos alpha t, just for some alpha. And that's going to be equal to this integral from 0 to infinity of e to the negative st times cosine of alpha t dt. Usually we'd think of something like integration by parts for this integral, but if we were to apply that here, we'd be doing it for a very long time. Though there is like a cool little trick once you do integration by parts the second time, you could like add something to both sides and divide, and then you get like this integral is equal to something. But we could also use this. Cosine of ax is equal to e to the power of axi plus e to the power of negative axi divided by 2. This could be derived from this equation, e to the power of ix is equal to cosine of x plus I sine of x, and then that could be derived from the power series of e to the x, cos x, and sine x. So this then just leaves us with the Laplace transform of e to the power of alpha ti plus e to the power of negative alpha ti divided by 2. Now we're going to take advantage of the linearity of the Laplace transform. We're going to take that 1/2 out and then split up this addition. So then we now have the Laplace transform of e to the alpha ti plus the Laplace transform of e to the negative alpha ti. Luckily for us, we already solved for getting the Laplace transform of these exponentials, so we could just apply that formula here. So let's recall our formula real quick. We have 1 over s minus alpha. So in this case, our alpha is going to be alpha I, and in this case, our alpha is going to be negative alpha I. So then we are left with 1/2 times 1 over s minus alpha I plus 1 over s plus alpha I. This is now our Laplace transform of cosine of alpha x, or cosine of alpha t, I mean. Something we could do to this is just keep that 1/2 out in the back. Over here, multiply by the conjugate on the top and bottom. So we have s plus alpha I over s plus alpha I. And on the right, again, multiply by the conjugate so that we have s minus alpha I over s minus alpha I. This then gives us s plus alpha I plus s minus alpha I all over s minus alpha I times s plus alpha I that could then be simplified to 1/2 times 2s over s squared plus alpha squared. Also, we can just simplify this to s over s squared plus alpha squared. Our next example is going to be with the Dirac delta function. So this is a weird function. It kind of just looks like this. Let's say this is our x-axis. There's just like an infinitely tall spike located at x equals alpha. And this is the graph of the Dirac delta function of x minus alpha. So at x is equal to alpha, there's a spike that is infinitely tall, but the area under that spike is equal to exactly 1. So now if we take the Laplace transform of this Dirac delta function, we have this integral. Now this Dirac delta function is like kind of like just like a weird tool that we use for integrals, and this integral just ends up being e to the negative s times alpha. This is kind of weird to wrap your head around at first, but that's kind of just like, think of it as like this is just like some tool that we use when integrating, and the Dirac delta function is 0 everywhere except for at x or t is equal to a, where there's an infinitely tall spike with an area of 1 underneath. So when we multiply this function with the Dirac delta function, or really just some function with the Dirac delta function, it ends up just being the function evaluated at wherever that spike is. And that's why we're left with e to the negative s times a. Next, we have the Heaviside step function. So what this function looks like, it's just 0, constantly 0, until we get to t equals alpha, where it then just immediately jumps up to a value of 1. This could be modified, so let's say we had 3 times mu of t minus alpha. This would then look like kind of the same thing, except it jumps to 3. So now let's take the Laplace transform of this. We'll have mu of t minus alpha, and that's going to be equal to this integral from 0 to infinity, e to the negative st, and then mu of t minus alpha. Now we know we are able to split this integral up, so let's split this up from an integral from 0 to alpha of e to the negative st mu of t minus alpha, plus the integral from alpha to infinity of e to the negative st mu of t minus alpha. Since the step function is just equal to 0 for this portion, we're just going to end up with 0 over here. So now we are just left with this. Since we know from alpha to infinity, the step function is just going to be equal to 1. We could rewrite this as the integral from alpha to infinity of e to the negative st times 1 dt. And that's just the same as the integral of from alpha to infinity of e to the negative st dt. Now we just have to integrate, so we have negative 1 over s, and then we have e to the negative st. Our lower bound is going to be alpha, and our upper bound is going to be infinity. That brings us to negative 1 over s times, well, at infinity, we're heading towards 0, so that's going to be 0, minus e to the negative s times alpha. This then just leaves us with e to the negative s times alpha over s. And that is equal to the Laplace transform of mu of t minus a, which is the Heaviside step function. If we do have something like this alteration to the step function, where let's say we multiply it by 3, and then now we're jumping up to 3, we just use the fact that the Laplace transform is linear, so this would just be equal to 3 times the Laplace transform of mu of t minus alpha. Okay, that's all for this video. If you found this helpful, that's amazing. If not, please let me know what I could have done better. I will soon upload a video on doing inverse Laplace transforms and partial fraction decomposition, so that'll be coming soon. Thank you for watching.